As global warming increases its impact on polar ice caps, it's important now more than ever to understand iceberg melt dynamics. We have modeled these dynamics using two rotating DIY dynamics tanks of different salinity water with an ice cube in each to mimic an iceberg. The rotating tanks mimic the effects of planetary motion on ice-ocean dynamics. The tank on the left contains fresh water that is warmer and therefore less dense than the cold ice water melting from the Icecubergs. The meltwater, shown by the blue dye, sinks to the bottom and forms vortices due to the rotation of the tank. When we look at the tank from the side, we can see that the cold Icecuberg melt is denser than the fresh water surrounding it and sinks in a helical pattern in the tank. As the meltwater sinks lower in the tank, it disperses outward and spins slower compared to the top of the tank due to the law of conservation of angular momentum. The sinking meltwater also draws in water near the surface. This fluid spins fast in the tank, also in order to conserve angular momentum. The resulting helical columnar flow below this Icecuberg, with a faster so-called prograde swirl at the top and a slower retrograde swirl at the bottom, is called thermal wind flow. The Icecuberg in the freshwater tank superrotates because it becomes entrained into the surrounding superrotating thermal wind flows that exist at the top of the cone of meltwater. The density differences between the dense meltwater and the surrounding freshwater, coupled with the Coriolis effect due to the rotating tank, cause the iceberg to spin faster than the tank. We hypothesized then that the thermal wind flow applies torque to the icebergs, causing them to superrotate. The tank on the right contains saltwater that is denser than the Icecuberg melt. Therefore, the less dense meltwater, shown by a blue dye, stays near the surface and forms a stably stratified capping layer that floats above the deeper saltwater. There is no superrotation in the saltwater tank due to the lack of thermal wind flow in this thin sheet of meltwater. This top view really shows you the effects that stratification has on the melting rate of ice cubes in freshwater versus saltwater. The saltwater ice cube has approximately 4 times more surface area on its skyward side because of stratification protecting the Icecuberg from warm surrounding waters. These experiments seem to indicate that meltwater sinks, forming vortices below icebergs in fresher waters, while in more saline waters, it forms a stratified capping layer that has the potential to limit exchanges across the air-sea interface. Ultimately, understanding iceberg melt dynamics and how they distribute their meltwater across the ocean is vital for creating accurate climate models for oceans where ice is present.